Welcome to the B-side to chapter 4 of my little online course on COBOL. In this video I want to show you how to write a reverse shell in COBOL, and the purpose of this is to understand how we can interact with C library calls from GnuCOBOL and also model some more complex arguments that are handed from COBOL to C. Now, perhaps you don't know what a reverse shell even is, so let me quickly tell you that. A reverse shell is a program that hackers or security analysts use as a backdoor to some remote machine. So we will refer to the person using the reverse shell as the attacker, and the machine that is running this backdoor is the target. The attacker starts the listener on his or her own machine on a given port. And for example, possible programs you could use for that would be netcat or metasploit. I will be using netcat, which is on macOS available with the nc command, on Linux probably too. And when the reverse shell runs on the target machine, it will try to connect back to the attacker's machine. And then it runs a shell process on the target machine whose input and output get redirected to the remote port on the attacker's machine. So once this connection is established, the attacker can then use the shell to execute commands on the target. For a reverse shell on Unix-like systems, such as macOS, Linux, or all the different BSD flavors, we can use the POSIX sockets API, which is provided on all of these systems written in C. The steps we have to do to create a reverse shell are the following. First, we create a socket, which is a computational abstraction for a communication endpoint. And this can be done by a system call that is aptly named socket. This will give us a socket descriptor for this newly created socket. And together with this and the connect system call, we can connect the newly created socket to a remote IP address on a given port. So here I will use 1234 as the port number running on just my own machine. So I will just connect back to my own machine for the sake of demonstration, but you could imagine any remote IP address in principle being used there. What we then do is we duplicate the socket descriptor to replace the file descriptor for standard input, standard output, and standard error, so that all input and output and error messages on the terminal are redirected to our remote socket. And for this we can use the dup2 system call, and only on Linux systems it actually has been replaced by the dup3 system call. And finally we execute the binary for the shell. So in our case I will be executing the bash shell, and this can be done with the system call execve. And this happens in the original process that is running the reverse shell. So the input and output for the shell we create here will be redirected to the socket we created in the second step, because we duplicated the corresponding file descriptors in the third step. And I'm not going to give a very detailed description of reverse shells in this video, but if you want to learn a little bit more about how they work, then please check out my video Shellcode for macOS on M1 chips, part 3, writing a reverse shell, where I will write such a shell in ARM64 assembly, and it contains a little bit more detail than this video here. Before we begin, let's just check what we have available in COBOL, more precisely in GnuCOBOL. And when we're trying this out, it comes as quite a pleasant surprise that we have access to the complete C standard library and the POSIX libraries from GnuCOBOL without the need to give any additional parameters to the compiler or explicitly link them or include any files explicitly. That's very nice. And I'm not sure if this is just a macOS thing, because all the libraries are bundled in the shared dynamic library cache. I haven't tried it out on Linux, but at least on macOS it works very smoothly, and we don't have to do anything in addition to get access to the POSIX system calls from GnuCOBOL. In particular, we can use COBOL's call instruction to call all the functions in the POSIX socket API. And before we begin, let's quickly recall how we translate C data types into COBOL data types. We already had this in chapter 4, but for this video it's important to remember it. So this is the table of C data types, and here how COBOL data types would correspond to it. In particular, what we will need is that individual bytes or characters can be modeled with the alphanumeric data type in COBOL, where each X or each number here, each character corresponds to precisely 1 byte in memory. And integers in C can be realized by numerical data types in COBOL that have between 5 and 9 digits. And I will just be using 8-digit data items for integers in the following. The reason for that is, well, first of all, it's in the proper range here, and also with 8 digits, it would also work for other COBOL dialects than just IBM COBOL, even though everything I will be writing today will be IBM COBOL. So let's begin. The first thing we need to do is to create a socket, and for this we use the call socket return value int with 3 parameters: domain, type, and protocol. So domain is the protocol family for our communication, and we will set it to the value 2, which corresponds to the constant pfinet, which symbolizes IP version 4. Type I will set to 1, and this corresponds to sockstream, which indicates that we want to use the TCP protocol. And finally, the last parameter is not really necessary anymore. Once we've settled for TCP IP, we will set it to 0, which is a dummy value that is also used for the IP protocol. The return value of this call is an integer, and this will be the socket descriptor that we need to establish the connection in the following. So we need to save this return value. Now, all these arguments and the return value are integers, so I can define them in COBOL as data items of type pic 9 with 8 digits, usage binary. This is what it would look like in COBOL, and now let's begin to implement our reverse shell. Here's the COBOL program in which I will construct my reverse shell, and first I will type out the arguments for the socket system call. They're all integers, so I will just use the 8-digit numerical type. And this will be my return value, socket descriptor. Also of type integer. But this one does not get assigned a value in advance, of course. And once we've declared our arguments and the return variable, then we can make this system call socket pfinet sockstream IP proto IP. And in COBOL, this is realized as follows: COBOL, the name of the call in quotation marks as a string, using, and here it's important we hand these arguments by value to the C function, pfinet sockstream IP proto IP, and return value will be the socket descriptor. This of course goes into the procedure division. this realizes our first call. So far it doesn't make sense to run anything, so we will leave that till the very end, that we try out running the program. Once we've created the socket and have our socket descriptor ready, we can make the connect system call, which has 3 arguments: socket, address, and address len. The first argument, socket, is just the socket descriptor we created in the previous socket call. The second argument, address, is a pointer to a structure of this sock_adder in type. This is 16 bytes long, and we will explain how it works in a moment. And finally, the last argument, address len, is set to 16, which is just the fixed size of this structure we pass to it in the second argument. Now this sock address in structure, which we give as the second argument, or the pointer to which we give in the second argument to be precise, has several components, and it looks slightly different in Linux and the other Unix flavors, but let me just walk you through it. So we have first a 1-byte field called sin len, then we have sin family, sin port, sin adder, and sin 0. In Linux it's a little bit different, so this field is missing, but the sin family is 2 bytes, and then the other fields are exactly the same size in Linux. Now let's look at these components. First, this field here, sin len, will be set to 0, and this is not even used. That's probably the reason why in Linux they removed the field altogether. The second, sin family, is the protocol family, and we will set it to 2, just like we did in the socket call. Now you may be wondering, why do we even distinguish these 2 cases here? Why don't we, if we ignore this part anyway, why don't we just treat this as one 2-byte field for sin family? Well, the reason is that if we assign the value 2 to this byte here, or to this 2-byte entry here, then the byte order in Linux would actually be reversed. So the number 2 in Linux would appear in the first byte, whereas here it would appear in the second byte. So there's a very tiny incompatibility here between Linux and the other Unix flavors that you have to be aware of when you use this structure. And in the following, because I'm working on macOS, will be using this version here, but be aware it's very, very slightly different on Linux. Anyway, let's look at the other components. Next comes the port, 2 bytes long. This is the port for the listener on the attacker's machine. So we will set this to 1234, just because that's a number that's easy to remember and it's not used for any standard network applications. Then the address, 4 bytes long. This is just the IP address that we will connect to. In this case, I will set it to 10.0.0.13, which is just my own IP address. So I will be connecting back to my own machine for the sake of illustration. And finally, we have 8 bytes that are just filled with 0. So this is just a padding to ensure that the total size of our structure is 16 bytes. Now the first argument in this connect call is socket. So this was just the return value from the previous socket call, and we will just reuse that here. The third argument, address length, is of type sock_length. And if you dig a little bit through the source code of whatever Unix or Linux you're using, you will find out that this is just another integer. So in COBOL, you can represent this argument here, the third one, again by this COBOL type, the binary numeric type with 8 digits. For the sock_adder in structure, it's a bit more complicated, but with the table we had in the beginning, we can translate its component into the following COBOL types. So on macOS, the first 2 fields, which are just 1 byte in length, will be just an alphanumerical type in COBOL with 1 character each. Port, which was 2 bytes, can be represented in COBOL as a numerical type with 4 digits. The address will be a numerical type with 8 digits, and finally the 8-byte padding in the end, I will just use an 8-character alphanumerical type that I will fill with zeros. And in Linux, yeah, it's almost the same, only the first 2 bytes in Linux I will, well, if I were to program this in Linux, I would define it as the 4-digit numerical type, but I will just restrict myself to demonstrating this on macOS. So I will use this structure here. There's one thing you have to be aware of when you use this socket API, and that is that you're expected to hand the port argument and the address argument in big endian format. So that means the byte order of these 2 fields here has to be reversed as compared to the usual little endian order that you find on most machines. However, IBM COBOL already stores binary data as big endian by default. So in our program, we don't need to do anything. We don't need to think about how these values look in reversed byte order, because COBOL will do that automatically for us. That's convenient, and even more convenient than if you were doing it in C, but you have to be aware of it. With this, we can now implement our arguments for the connect call in COBOL. And remember, this is only the macOS version because I have these 2 1-byte fields here. In Linux, you would replace that by 1 single 2-byte field, syn family. And observe that to these 2 fields here, I will assign their values as hexadecimal numbers. And that is because usually you can only assign printable characters to the alphanumeric data types in COBOL, unless you do it byte-wise with hexadecimals. Then we have our value 1234 for the port, which is straightforward. And then we have this mysterious value here for the IP address. My IP address is 10.00.13. So if I translate that into hexadecimal, it would be 0A for the 10, 0000, and finally 0D for the 13. If you translate this hexadecimal number into a decimal number, then it just becomes this one here that we give as default value to our address. And here, sin 0 is just the trailing 8-byte block, which is set to 0. And I can do this in COBOL by making it an alphanumerical type with 8 characters and setting the initial value to the constant low values. So this will tell COBOL to initialize these characters here, or these bytes, with the lowest possible value, which is just 0. And finally, we have address length, which is just the 3rd argument for connect. And this is set to 16, which is the size of this data structure here. And then, once we've written down these data types, we can implement the connect call in COBOL by calling connect with by value the socket descriptor that we got from the previous system call. Then by reference, because it's a struct, to this listener address here, and again by value to the address length value, which is 16. The return value will be put in the special register return code because it's just a status number and I'm not interested in that, so I didn't declare an extra variable for it. So first we create our address structure as a record in COBOL. We have these 2 1-byte blocks. The first one initiated to 0, and the second one initiated to 2. Then comes the port. This will be a numerical type, 4 digits. One, two, three, 4. Then comes our IP address as a full integer. here we have this mysterious value that I will just copy in. And this is just my own IP address, 10.00.13, expressed in a decimal number. And finally our 8-byte 0 padding. Pick. With low values we can initiate it to be set to 0. This is an integer. And just to make it a bit clearer what is happening when we run the shell, I include a few output values here that I will print to the terminal that will indicate that now I'm connecting to a given port and address, even though the address will just be given in this decimal value here. So maybe it's not super helpful, but at least we can check that something is happening. Now we make the actual connect call using the 3 arguments we just constructed. First, by value is the socket descriptor, the one that we got as a return value here. Next, by reference, we hand our listener address. And then again by value, address length. And the return value will just be written to the special register, and we will not use it for anything after that. Then, once we have created our socket and we've made the connect call, we will move on to duplicating the standard input and output file descriptor to our socket descriptor. To duplicate these file descriptors, I will use the dup2 system call. It has 2 arguments, fd and fd2. fd is the file descriptor that is to be duplicated. So here we supply our socket descriptor, which we obtain from the initial socket call. And fd2 is the number of the new file descriptor. And this one we will set in turn to 0, 1, and 2, because these correspond to standard input, standard output, and standard error output. So by doing this, we will redirect all input and output to our socket descriptor. The return value here is the new file descriptor, but we have no further use for it, so I will not use the return value. And these are straightforward to define in COBOL, so I will define them as integers with values 0, 1, and 2. And then I can make the call to dup2 using our socket descriptor and in turn one of these 3 standard file descriptors. So I will make this call 3 times, once for standard in, standard output, and standard error. First, I will define my standard file descriptors. Next is standard output. One and standard error, which will be number 2. We can make the call to dup2 using as arguments our file descriptors, all by value. First our socket descriptor as the one to be duplicated, and then we begin with standard in. And we will do this 3 times, once for each of the standard file descriptors. So standard out, and as well, and that should do it. Now we have duplicated the file descriptors so that our socket, or all our input-output, is redirected to our socket descriptors, and what's left to do is to run the shell. To launch the shell, we can use the execve system call. So this one allows you to supply as a first argument a path name of the program you want to run, which in our case will just be bin bash. So we run the bash shell. The second argument, argv, is actually an array of pointers to string arguments, which is terminated by a null byte. Now we do not require any arguments for our shell call, so we will simply set this to 0. And similarly, the last argument is an array of environment variables, which provides some context for the executed command. We do not need this, so we'll also just set it to 0. What happens when you run execve is that it transforms the calling process into a new process running the bash. And this new process inherits the input-output file descriptors from the old one. So they will still point to our connection socket. Since the last two arguments for execve are both 0, I will not define any variables for them. I will just pass 0 by value to this system call. Now one caveat here is that path is expected to be a C string. So execve is a function that's written in C. So what it expects here for path is a null terminated string, because that's the way strings are handled in C. But COBOL strings are not null terminated because they all have a fixed length. So there's no reason to put a null at the end to indicate that the string is over. So we must wrap our COBOL string into a record where the actual string is followed by a null byte. And I do it like this. I call it path string. And the first component is the actual string as a COBOL string. So this is 9 characters long. So it's an alphanumeric type with 9 characters. And then I follow it by a single byte that I set to 0. So this is the terminating 0 for the C string that is required for this argument here. We could try to omit this and hope to get lucky that the memory following this string is set to 0 anyway, then it would work as well, but we should not rely on such a thing. So that is why we have to make this construction to wrap a COBOL string into a C string. And once we've done that, we can make our last system call to execve, which will launch the bash, and at that point we should have our reverse shell. So let's try this out. The first thing I do in the working storage section is my wrapped C string for the command that I want to run. So path, let's just do it. So this is a 9-character string for the call to bin bash. And then the terminating null byte that is required by C as a string terminator. And again, I will just provide this here as a 0 in hex to make it more explicit. I could use the low values keyword again, but I think just writing it out as 0 makes it a bit clearer what I'm doing here. And in the procedure division, we make our final system call to execve using by reference the path string, so the command that will actually call the bash shell, and then just the 2 arguments here, one for the command line arguments of which we have none. So we will just pass 0, and then the environment variables, which we also ignore. So another 0, and once again, the return value will just be some status code. So we will ignore it and write it to the return code register. And strictly speaking, the stop run is unnecessary here, because once this call has been made, the whole process will have been replaced by the bash. So whatever commands come after this will have no effect. And just for the fun of it, I will display something on the output. And this will confirm that I'm running the shell now, and this will then actually appear in the shell on the target machine. Okay, so that should be it. Let's compile this and then try out if it works as a reverse shell. The first thing I do is start my listener to netcat. The command for netcat is nc -l for listener, and then I give the port number. If this were on Linux, I would have to write p as well to make it explicit that I will provide the port number as the next argument, but on macOS you don't have to do that, or you actually shouldn't do that. So you don't see anything now, which is to be expected because there's no connection, but I'm listening on port 1234 now, and if I type any commands, you see nothing happens. If I type garbage, I don't get an error, so this just vanishes into the void because I don't have a connection yet. And now I will compile my reverse shell. And of course I have errors. Yes, so I get an error here because I forgot the value keyword. And I get an error here because I again forgot the value keyword. So a lot of values that I'm apparently missing. Let's fix those. Low values here. And then let's try again. So observe these two terminals and see what happens. I've connected, and you see that the commands I typed in before and the garbage I typed in before now have been interpreted now that I've got the connection. Maybe let's do something useful. We could find out what machine we're on. Yeah, so I get the system info if I type in uname. So now I can execute commands in my netcat shell here that was created in the other terminal. We have succeeded in writing a reverse shell, and in theory we could now install a backdoor written in COBOL on other people's computers if we were malicious. But of course we are not, so we would only do this for security testing purposes, of course. And also, you probably wouldn't want to use such a crude reverse shell anyway, but rather rely on some professional toolkits for that. Thanks for watching, and do not forget to like this video and subscribe to my channel. And see you soon for the next chapter of my COBOL course.